Oh, what I thought I'd do is first kind of go over again, say something about kind of what I said last time and some of the stuff that I said far too quickly last time, and then maybe stop and let me do that for a little while. And then if you have any questions about that material, please, any material from last time, if you can wait for that. And maybe there's some things that are still confusing about that. There's some very confusing issues about that stuff. And then I'll go on to the newer material, which is going to give you kind of a complete classification of the representations of SU2 and SO3. Okay. Okay. So let's go back to last time. So what the new thing last time was the spinor representation. Let's see. And as a piece of mathematics, this is really kind of trivial. It's kind of silly. It's just that it's a representation of the group SU2, and it's just given by pi of G is equal to G, acting. These are 2 by 2 matrices, so they act on C2. And so there's really, in the obvious way, and just from the definition of the group. So it's the so-called defining representation. So as a representation, this thing is really kind of trivial and kind of silly. And then, but then you also, if we're going to work with it, you want to also think about the Lie algebra, and we had using the basis of these x sub j basis. How did I want to write this? Yeah, I had that pi prime. Oh, you have, again, so pi prime of x in the same thing is just x, where x is some kind of 2 by 2 matrix that you can exponentiate to get an SU2 matrix. And in particular, we are interested in there's this basis of the xj's, which were given by minus I, then the Pauli matrices over 2. Okay. So now, so what do you have when you have this matrix? Let's see. Is what I'm doing here? I mean, saying that I've got C2 with SU2 acting on it. If you think about it at the level of the Lie algebra, all that I'm really saying is that I've got the Lie algebra representation is I've got C2 with the sigma matrices acting on it. So this is really exactly the same structure that I kind of wrote down when I started to say, if we've got if we just take the basic axioms of quantum mechanics and we have a two-state system and we ask what all the self-adjoint operators are, well, they're the identity operator, then they're the sigma matrices, the Pauli matrices. So so this is so we're recovering the same structure, which is just the Pauli matrices acting on C2, and that these are the self-adjoint version of the x sub j's that you get if you multiply by I. But now they carry a lot more structure. They're not just some random random sets of 2 by 2 matrices acting on C2, but they're things that when you exponentiate them, they give you SU2. They give you SU2 elements, and the really non-trivial aspect of all this is the relation to rotations and to and to SO3. So maybe one thing to say about this is that if you just think of this as the two-state system, I'll often refer to that as a qubit. And if you go and look at what people who are trying to actually make qubits do in order to design quantum computers, I mean, generically, if you look at some physical system that's supposed to implement a qubit, it's just going to be some random two-state system. Okay, and if you take some random two-state system, then what I said in that first lecture about two-state systems is really kind of all that this formula can say about it. But there's some, I mean, there are some two-state systems which actually, have this property of spin, and that they actually are described as a spin representation. And the thing which is different about them is that you get a relationship to actual to rotations and to angular momentum. And we'll talk a lot more about that. But the main example physically to think about is some kind of fundamental particle like an electron. If you take an electron and think about making it infinitely massive so it can't move and just look and see what it's going to do, it's going to be described exactly by this C2, but it's not, and the observables that are acting on it are not just kind of random observables coming from nowhere. They're tightly connected to infinitesimal rotations. These things come from infinitesimal rotations. So that's the I wanted to say. So the let's see. So the new thing here, that's really subtle, is the relation to SO3. That this guy is that SU2 is kind of has this homomorphism taking you down to SO3, and I'll sometimes write it like this, that it's got a Z2, that each point in here corresponds to 2 points in here. So the kind of new thing about this, about these matrices acting on C2 that we have here is that this is actually a representation in some sense of rotations, though it's kind of rotations plus an extra little piece of information somehow. So you can think about normally you think about rotations in terms of SO3, but you can think of them in terms of SU2s. But then you have this somewhat mysterious fact that there's kind of an extra. There are 2 of these for each one that you already know about. And that if you go around a circle down here, if you rotate it in a circle down here and look at the corresponding ones up there, you only kind of go halfway around the group. You go from 1 to -1, not all the way around. So it's a weird. This is a weird. Anyway, so these guys kind of in some sense are acted upon by rotations, but in this weird way by this enhanced versions of rotations, not rotation. So that was the main thing about last time. And so let me okay, so then let me say something more about the relationship to physics, about especially for physics. I mean, so most of what I was saying, the easy part of what I was saying last time was all just the stuff about, well, just look at these matrices acting on C2, you exponentiate them, you get SU2 matrices. And but the interesting thing is that this has a lot of non-trivial relation to physics, and I want to I think the thing that you can write down that I talked a little bit about the action of what happens in a magnetic field. Let me put that in a little bit more context, especially for people who haven't seen this before. So what we're going to do after the exam. So after the exam, we're going to go to a theory of a free particle. Okay. So far, everything we've talked about in this course, there's really not enough degrees of freedom, to talk about something that's moving, because something that's moving can kind of be in an infinite number of places at once, and these finite dimensional state spaces are not going to ever tell you about that. So we'll talk about theory of free particles and about wave functions after the exam, the next part of the class. And then what happens is if you have a theory of a free particle, you can imagine introducing forces and talking about forces acting on a free particle by you could introduce coupling to magnetic field to electromagnetic. So besides talking about a free particle just running around, you can talk about what happens if you have if your particle has a charge and you've got some kind of background electric and magnetic field, which is described by these two electric field vectors, magnetic field vectors everywhere in space and time, and then you can ask what this particle is going to do subjected to those fields. Now, one thing that you find, and so this is a story that we'll get to, I think more, actually might only get to this more kind of later when I start at the beginning of the second part of this class, or maybe, I forget actually where I do this. But anyway, so the simplest version of this, if you have what's called a scalar particle, you can have particles which have no kind of, which are just described by at any point by a complex number, and then you can couple them to electromagnetic fields. But you can, it turns out you can, the actual elementary particles that we know about, like the electron, for instance, the way that they're actually described by wave functions, but wave functions at each point are given by one of these C2, by this C2. And then you can, so if you couple one of these, something like an electron, which is called the spin one half particle because of the way SO3 acts on this, SU2 acts on this guy, then you get and you couple it to the electromagnetic fields in the standard way, which we'll discuss. Then what you find is that, you know, how the thing is going to move and how its C2 degree of freedom is going to evolve depend upon the magnetic field that it's in. And so what we want to do, so the kind of simplified version, I want to talk about the simplified version. Is a fixed spin half. So, you know, in a magnetic field. So if you imagine, and so this is actually something, you know, quite, and this actually does correspond quite closely to actually some things that you might want to do that would to make a qubit. You want to somehow, you don't want this thing moving around. You're not interested in its degree, in its you know, in its space, you know, in its spatial degrees of freedom. You're interested just in this degree of freedom. And what you do is you somehow fix the particle or look at very massive particles, and then you choose some kind of background magnetic field, and then you ask what's that gonna do to this guy. And then let me see what okay, and then so what happens then is you get let me then say what happened. I want to say this. Okay, so this is a fixed spin half particle. So, yeah, in background magnetic, and so it's something. Field. Okay, but so a general magnetic field will vary in space and time. But what we're going to assume that if the thing is fixed, we only need to look at the magnetic field at one point, and we'll assume for that first we'll assume that it's constant. And then so you've got so then the only question you can ask is if you know what the initial state of the system is, how's it going to evolve? So if you know where you are as a vector in C2 at time 0, how are you going to move around in C2? And that's the Schrodinger equation, is then this I dt psi is H psi, and H is H is just a linear combination of the self-adjoint operators we know about, the Pauli matrices, with these guys, and the particular combination that comes out in the out of this more advanced theory of electromagnetic coupling is that you get. Let me write. I'll write it this way. So it's G E over 2mc. I got this right, and then E1 sigma 1 over 2. So it's just this. So these guys then just become the coefficients of of an arbitrary self-adjoint operator on C2. Okay, and then you can solve this thing. So the solution is just psi of t is equal to, you just exponentiate. So the I gives you minus I here. You just exponentiate that minus I t h, and I'm assuming, and so in the simplest case, this is constant in time, and you get this. This is the solution, and so I'm going to write it this way. Okay. So to solve these problems, you just need to be able to exponentiate these guys, and this is a problem that especially if you think of them in terms of. Anyway, a lot of the manipulations I was doing about thinking in terms of quaternions and stuff, a lot of it was devoted to kind of just to understanding the formulas that you get when you exponentiate these guys. That these guys behave kind of like. Anyway, I think there are various versions of that calculation which we went through, and a lot of them were motivated just by the fact that we wanted to. A crucial thing was to be able to calculate these exponentials. Okay, and then what you find, one thing that you find, and you find, okay, so if you were, if this was just a general two-state system and a general 2x2 self-adjoint matrices, then the solution would be what it was, but it wouldn't really have any connection at all to geometry. But if in this case where you're where we're thinking of this degree of the C2 degree of freedom as being a fundamental spin one half degree of freedom, which is carries some relationship to rotations. Then what you find is that what's the formula to say? Well, that exponentiating this guy, you're basically exponentiating this b vector times the dotted with the sigma vector. And if you look at the formulas that I gave for how to calculate a rotation, how do you calculate? So remember that if you wanted to, anyway, remember if you go back to the quaternion language, and w vector was a unit quaternion, then e to the theta w vector was the rotation. I theta about w vector, right? So this was one of the things that we found when we were looking at quaternions, and you could translate this, instead of thinking of these as unit imaginary quaternions, you could translate it into this language. And then what you find is that so this exponential here is you can interpret this action as this kind of rotation action. And so this corresponds to, so this is the rotation action. Well, this corresponds to, let me just say this, to the rotation by an angle, let's say, sorry, at a constant rate. About the vector or b vector. So if the if you look at what this formula is telling you, it's telling you that you're gonna you're doing the same calculation as you did as if you were rotating, as if you were trying to ask the question of, okay, I think this is about something it's a representation of the rotation group of this enhanced version. So it kind of rotates. And if I'm doing a rotation about this axis and this angle, what's going to happen? Well, the calculation is exactly the same as this one, except instead of an angular variable theta, you have a t. And so what's happening? So you're kind of moving. You're doing some angular thing at a constant rate. And the vector that you're the analog of this guy here is just your b vector. So you can anyway. So the answer that you get when you solve the Schrodinger equation, it has kind of a nice geometrical interpretation, except it's a weird one because it's talking about rotations not of an object in space that you know about, or vectors, but rotations of this weird spinor degree of freedom. But what you learn is, if you want to know what a magnetic field, a constant magnetic field does to a spin 1/2 particle, if you hit a spin 1/2 particle with a fixed magnetic field, it just causes it to evolve in time, in the same way that it would with a rotation about the field, magnetic field vector. Okay. And then maybe let me just say a couple more, maybe a few more things about physics. And then stop this. So so that's. That's one piece of physics, and it all kind of comes down to this simple calculation. But maybe another. Okay, so let's do one other thing. So another thing is note. So let's think. So note. Well, let's say this. Let me call this just let me give it a name first, but before I explain it to you, called the Zeeman effect. And maybe it's good to explain it. What people saw is that when they were measuring the energies of atomic states by looking and seeing what happens if you hit them with some light, and you see and you look at the frequencies of light that get radiated back, and you can measure the energy states of an atom. What they found was that they'd see certain energy states, and then some energy states, and then if you increase, you put it in a background magnetic field, and you increase the size of the magnetic field, and then you would then see a splitting, and you would see the original. You would see two states. You would see a state with a bit more energy and a state with a bit less energy, and you would find that as you increased, so the spacing linear in B vector is that as you increase the strength of the magnetic field, the spacing would get bigger linearly. And so this was called the Zeeman effect. And you can understand where that's coming from. You can understand that as coming from exactly the problem that I was talking about. Because if you take, so let's see how to understand that. Why this should happen in terms of that this is exactly what you're going to see in the case I talked about. So let's do the. Well, let's do it this way. Let's take, so let's consider B vector, in the is vector E3. In other words, let's just take choose the 3 direction, or the Z direction be the direction of the magnetic field. And then you can kind of ask, what are the eigenvectors? Okay, and then since sigma 3 is 1, minus 1, 0, 0, the eigenvectors of H are the eigenvectors. In this particular case, because the only the other terms are 0. The only term you have here is something proportional to this. They're the eigenvectors of sigma 3, and they're going to be 1, 0, and 0 and 0, 1. Now, if you look at anyway, so if you look at what H does here, I guess that if I wrote this, I can say H on. So you're gonna have H on applied to the to this guy is going to give you GE over 2MC, and then you've got a B vector, and then it's a sigma 3 over 2, so there's another half. Okay, and then applied to 0, 1, it's going to be the same. It's going to be the same thing with a minus sign, because instead of a so instead of this one here, you pick up this one here, and so it's minus. Okay, and so there's a splitting. So what you expect to see is you expect to see a splitting by this amount. Okay. So you expect to see, just due to the spin 1/2 degree of freedom and the way it interacts with the magnetic field, you expect exactly what's seen there, which is this. So that's another piece of physics. Okay, and then I think maybe the last thing to tell you about is a little bit about the this system is often used to discuss kind of the subtleties of measurement theory, and maybe to say a bit about kind of what that means maybe in practice a little bit. Okay, so this is Zeeman. Now let's go. Stern-Gerlach. Perfect. So this is a bit more complicated, so I won't be able to kind of write out the full to explain to you. Given the way we're treating fixed particles now, I kind of can't quite really write down the equations for exactly how this works. But let me tell you the basic idea is that you've got you have some kind of magnetic field. So imagine this is some there's some magnetic field, and you've got a particle moving through it, and depending on on the geometry, what's going to happen is that what you observe happening if you take some beam of spin half particle of charged spin half particles and put them in some apparatus like this, is you find that there's these things that the beam breaks up. The magnetic field causes the beam to break up and go in 2 different directions. So you find the particles. Anyway, you roughly see that. Wait a minute, half of the particles are being sent one way by this magnetic field, and half are being sent the other way. And it turns out that this is if you actually have a full theory of how these things move, that is the effect of a magnetic field is going to actually change the way that they move, not just change their energy and change and rotate the internal degree of freedom. It's actually going to change the spatial degree of freedom. So let's say that if you get the geometry right, things that are proportional to this are going to go. Yeah. Anyway, things that are proportional to this are going to go this way, and things that are proportional to this are going to go this way. So one thing that you can do, especially as a thought experiment, this is a favorite thought experiment in physics books to think about. The whole problem in measurement theory is that if you just take some random beam here, you really don't know. You really don't know what's going on. If somebody just feeds you spin half particles, and you don't really know exactly how they're made or anything about them, then you really don't know. Anyway, you don't know what their state is. Is it can it it's some linear combination of these guys, but what linear combination of it is, who knows? But on the other hand, what you can do physically, if you look at what this is doing, you can then make this you can then split off this beam and use this beam of particles. And this beam of particles, because of how this happened, you know that the state. So here, psi. Let's take if time zero is there, is proportional to 1, 0. So we know that this is a beam of kind of ups. We'd like to say this is a beam of upspin particles, and we could so if you so if you think of this apparatus as what it's doing is that it's measuring the spin in the z direction of the spin of the particle, and when it comes out here, it's giving a +0.5. When it comes down here, it's giving -0.5. And then what happens then you find is that if you do this again, you get the same thing. So if you put it through the same apparatus, it does the same thing. So this seems to be it seems to have a stable property of having plus spin 1/2, and if you keep on and putting it through the same kind of apparatus, it will always go up. And this is great. And similarly here, you put this through the same apparatus again, it'll always go down. So you would like to say that that this is a nice stable property, like a classical property that you can assign to these guys. But the problem is that the real problem with quantum mechanics, though, is that this, since these spin operators are non-commuting operators, the ones for different directions don't commute. That if you take the spin through the Pauli matrix 3, it doesn't commute with Pauli matrix 1 or Pauli 2. That the other thing you could ask about is what happens if I rotate. What happens if I take this and rotate it so the z direction now becomes the x direction or something? So if you look at the rotated version, rotated. Well, let me put it maybe to make it even a little here. Let's say I rotate this by some amount. I'm gonna find again that it's gonna split again. Okay. And you're going to get different. You're going to get different. You see two possibilities. Abilities with different probabilities, and these are Born's rule. Tells you how to calculate them. So if you re-express this guy, if you rotate this somehow to some different direction, and then rewrite this guy as a linear combination of eigenvectors of the spin operator in that other direction, you're gonna get some linear combination of these guys, and that linear combination, the norm squareds of those coefficients are going to tell you how likely you are for it to go in one direction or another direction. So this is this I think may be kind of one of the ways of seeing the core of the measurement of the measurement problem. That really what you thought you had here was that you had something very simple that you had a complete description of, that it was this guy. And so you have something completely simple which you think you have a complete description of. You then do something which you think of as measuring something about it, and all of a sudden it starts doing completely different. It does completely different things and all you can. The only thing that knowing this told you and knowing the rotation is that it tells you the different probabilities of different things happening. So you've gone from some nice deterministic thing following this which evolves according to this nice deterministic Schrodinger equation we wrote down, and then all of a sudden you've got a final state which you can't anyway, which if you try and think about these two things as some kind of stable characteristic of the state, they're you've evolved from one stable thing to just the probability of two different things. So that's I don't want to kind of say any more about that, but this is just to show you the connection even between the very simple mathematics we've been looking at, which is just 2 by 2 self-adjoint matrices acting on C2. Just the fact that different ones of these things don't commute, and the implication of that, if you're going to say that the things that have well-defined physical properties are the eigenvectors, well, you get this very weird thing due to the fact that you've got, and this is going to happen whenever you have operators that don't commute, so you can't simultaneously diagonalize them. Okay, so maybe let me stop at that. Okay, so let me stop it with this now, and I think I'll get off this topic and get away from this physics and go back to the and start on the new mathematics I want to do. But maybe are there any questions about this, either about the math or about the physics?
Yeah. So just to make sure I've got this right, Professor. So in this experiment, we split a beam of spin 1 particles.
Spin
with
half.
A magnetic field.
Yeah.
Sorry, spin 1 half. My bad. And they split in half.
Yeah.
And then if we iterate that process, they will seem to be stable unless we now put them through a slightly rotated field, in which case they will split once again.
Right.
What if we were then to put one of those beams through a magnetic field of the original orientation? Would it split again, or would it maintain the?
It'll split again. Yeah.
It will keep.
Yeah.
Keep
So what happens? So each of these guys now. Again, these guys are eigenvectors of some matrix corresponding to the new direction, and they're going to have a stable property of that direction. If you measure that direction again, you will get a stable thing. On the other hand, if you go back and go back to here which is a different thing, again it'll split again. Yeah. So you really cannot think of this thing as it's moving around as having, as having some kind of spin vector that lies in C2 that is anyway, that's not the way. If you try and assign physical significance to the eigenvalues of this thing, it's just not that's just not the way it works. They don't have a stable significance. It's on the one hand, it's physically very, very weird. On the other hand, it's mathematically extremely simple, and this is why you'll often see discussions of this paradox about exactly in this thing, because you can see the problem mathematically very simply, even though the physics is definitely weird.
Professor, I just want to make sure. So, I mean, suppose you have a magnetic field in Z direction for the first beam. Then, after you measure the spin direction of this, you have a fixed either spin up or spin down value in the Z direction, right?
Yeah.
Then, suppose you rotate the magnetic field to the X direction.
Right.
It splits again because those eigenvalues are not the eigenvalues of the spin matrices in X direction. Is that correct?
Not eigenvectors. Yeah. Yeah.
So, yeah. Okay. I just want to make sure. Okay.
Yeah.
Thank you.
And so what happens if you actually take I mean, because of the fact you can play with this and these are the eigenvectors in the 3 direction. I mean, you can play with this very simply and see what the eigenvectors in the x direction of sigma 2r and of sigma 1, and then you can see what happens when you rewrite one of these guys in terms of the others. But in particular, if you do kind of a 90-degree rotation and move from the z direction to something 90 degrees, then you get that this guy is some linear combination of things where the magnitudes are the same of the other 2 eigenvectors. So then it will exactly half the time it will go one way, half the time it will go the other way. But if you do some other random rotation, then there'll be some different numbers. Yeah. Okay. Any other questions about this stuff, especially about the physics? Anyway, okay. But this is, I mean, this should strike you as, I mean, as kind of weird or as kind of mathematically very simple and physically very weird. So, and I guess, I mean, when you try to think about it, the one thing that kind of bothers me about about all of these arguments is that, you know, what you're doing when you say that, oh, I'm often, the way this problem is formulated, you're saying that I'm just doing something very simple. I'm just measuring, I'm measuring the spin in the plus or minus z-axis using this kind of thing. But if you sit down and think about, wait a minute, what am I actually really doing? Well, what you're doing is you're taking this spin degree of freedom, which actually is much more complicated because it has all this space-time stuff. You're coupling it to some very, very complicated system, which you're trying to treat in some classical approximation, and then you're getting probabilistic outcomes. And part of the thing that yes, it's true. You're starting from something you seem to completely know about to something you only know about probabilistically. But on the other hand, the experiment you're doing, from the point of view of as a quantum state, you only really you actually never knew exactly what this magnet looked like as a quantum state. You only kind of knew about it probabilistic. So the thing that always, I should say, bothers me about this argument is that it's telling you that, if you think of measurements as things you do by coupling to these things you're going to treat classically, then you end up with a paradox. But what you'd really like to do is you'd really like to use quantum mechanics to treat the whole thing, and to also treat the experimental apparatus of this. But the problem is that's too hard. Nobody really knows. It's very, very hard to do that. So anyway, so hiding behind a lot of these paradoxes and the arguments about them is the fact that you're making some kind of approximation that of some classical limit, which is kind of exponentially complicated and actually hard to understand. Your thinking is easier to understand. But anyway, let me just stop with that. Okay, so let's stop with this. Let's stop with physics and get on to onto some new mathematics. Okay, so this is. Okay, so let me let me first explain what the question we're trying to answer today is, and then say kind of what the answer is, and then we'll start to go through the technology you need to get to that answer. And but it's this. So remember. So recall. So that we asked the question, what is, if we have some representation of U1 on a complex vector space, how can we classify all the possible representations? And the answer was, well, any representation can be broken down into one-dimensional pieces. And so, so any representation is just something built out of one-dimensional pieces. And then there's a list of the possible one-dimensional pieces. And those are the irreducible representations. So the irreducible reps of U1. What they were was they were given by something I'll call a map called pi n, and they're all one-dimensional. They're all on C. And then pi n was the map from U1 e to the I theta to some kind of linear map operating on this guy, and it turns out it has to be unitary, and it's just multiplication by e to the I n theta. Okay, so this was in some sense a construction of all representations of U1. They're just you can break them down into one-dimensional pieces, and on the one-dimensional pieces, this group element goes to multiplication by this number, by this guy. Okay, so that was easy. Now, what about SU2? SU2 all of a sudden becomes much harder. So would like to list, let's construct all, I'll often write irreducible representations this way of SU2. So that's the plan. Okay, and now let's say the the answer. So the list is going to be it'll be pi n, and it's going to act not on one-dimensional representations, but on representations of c to the n, so of n plus one dimensional. So the nth representation will be n plus one dimensional, and you're going to have n is equal to 0, 1, 2, etc. So you're not going to get negative n's, and you're going to get the non-negative integers, not the integers. So this is the list, and what we're going to have to do is figure out what actually is so we want, well, let me just say this. So we want to do a couple things. We want to first show that these are the only possibilities, and then actually get our hands on what these homomorphisms are. What exactly are these maps pi n? And and we've seen so n is equal to 0. This is just pi 0 is just the trivial representation. Okay, so whenever you can always take acting on C just by if you take the linear map, and if you feed it an SU2 matrix, you just get the idea. You just act by multiplication by 1. So that's really boring, but you always have that representation. Okay. Then we've seen n is equal to 1. So we saw a representation, irreducible representation, the spitter representation for n is equal to 1. That's on C2. So that's pi 1 of g is equal to g. So that was just the defining representation. And then we've got n is equal to 2. Actually, we also saw this. So we saw an irreducible representation of SU2 on C3, which was the adjoint representation. So pi 2 of g was equal to the adjoint representation. Okay, so this was just the representation of SU2 on its Lie algebra, which was 3-dimensional. And then we also saw that there's also the funny fact that this representation, if it's actually a representation on a real vector space. It doesn't, it's actually, you could complexify it if you want and get a complex representation, but it really kind of by definition acts on R3, not on C3. You can make it act on C3 by taking complex linear combinations that are real linear combinations and everything, but it's naturally defined on R3. And as a representation on R3, it's also the you can think of it as phi of g. Remember there's this homomorphism that takes SU2 to so this is an element of SO3. 3. And now think of this, as acting on R3, acting on R3. So there are various ways of thinking about, what this map is, but to see that it's going to be a little bit tricky to get your hands on. It's going to be, it really is going to carry the information about this interesting double cover map from SU2 to SO3, and it's going to naturally act on R3, though just by extending, by extending your scalars from R to C, you can get attacked on the same formulas work on C3. Okay. So this is what we've seen. We've kind of seen this. So the question is really, how do we show that how do we understand the rest of the story? How do we show that you can actually keep doing this, and how do we actually get a construction that will actually give us, that we can actually, for arbitrary n, we can understand what this map is going to look like. And you can kind of see that it starts out, completely trivial and goes to pretty much trivial, then starts to get interestingly complicated and subtle, and then it gets, if you try and think about it by this question of, how am I going to construct these homomorphisms, it becomes an arbitrarily very, very complicated story as you go to higher n. Okay, but now let's do, so what I'm going to do, maybe before I do this, let me make some comments about what's in the book if you start trying to read this. So, well, maybe let me make the comment more as I go along, as we get to this, because it starts out that but I want to say that the technique that we're using here to analyze this problem actually generalizes to general compact Lie groups, or to general complex semi-simple Lie algebras. So certain specific kinds of Lie groups and specific kinds of Lie algebras, you can completely solve the problem of classifying their finite dimensional representations using a slight generalization of the same methods. So we're actually, this is kind of the first big step in the general classification theory, and there's some more intricacy comes about, and the intricacy that comes out that we often teach in like a graduate course is it's in some sense has to do with the fact that for bigger groups or bigger Lie algebras, you have to think of them as having a bunch of different SU2s sitting inside them of different kinds that are tied together in different ways, and you have to understand how to break everything down into SU2s and understand how the SU2s are interacting. But that's a much more complicated story. But the SU2 story is already, moderately complicated. But it comes out. I mean, you can see the answer we're going to get was what I wrote down there, and it's not that bad. But here, okay, let's see the. Okay, so what do we do? Okay, so the first idea is to pick. So what we pick a U1 inside SU2, and then look at and study the representation, study pi restricted. Let me write it this way, so it's going to be then pi of G, well, pi just restricted to U1 of the. Okay. So in other words, if you have a representation, you can just restrict it to this subgroup. And the point of and the thing is, we actually know what all the possibilities are here. So we know. We don't know much about these pi's in general, but if we restrict them to this subgroup, then we know that they have to break up into these one-dimensional pieces labeled by integers. Okay, and so the standard thing to do is to choose. The simplest choice is to choose either the I theta or the minus I theta as your elements of U1. Okay, so you use the fact that diagonal matrices are gonna behave nicely, and you pick this subgroup, and then what you do is you show that then so then pi, and then what you find is that pi restricted to this u1 is going to be equal to pi for some q1 plus pi q2 plus qn. And so there's just going to be some integers. The qj are there's going to be some collection of integers, and and each of these is going to be on. All of these are all on C, right? They're all one-dimensional representations. So when you take an arbitrary representation and restrict it to the subgroup, it's going to split into a. I mean, it's going to diagonalize in this way. You're going to get this. Okay. And then so now then there's the next thing you do. Oh, and maybe we could actually see this. So for pi 0, you get just you get the same thing. You get pi 0. You get this axon. This is C with q1 is equal to 0, and then for pi 1, you get C. This is on C2. You get C plus C with Q 1 is equal to plus 1. Q2 is equal to minus 1. And then if you do this for that three-dimensional guy, you find C plus C, C plus C. It splits into three one-dimensional pieces with Q1 is is 2, Q2 is 0, Q2 is minus 2. That's Q3 is right. Okay. So the list of these numbers are called so the QJ are called the weights. So whenever we talk about a representation as having certain weights, it's just the integers that appear in this decomposition according to to this, and anyway to this thing that we picked. Okay, so then so in some sense the problem then, one aspect of the problem is to ask what are the possible weights? What are the possible patterns of weights? And one thing you can see here is that the pattern is pattern is symmetric under under interchange of sign of Qj. And so let me kind of what are the possible sets of weights in an irreducible representation. And one thing that you do is you show that so for one trick that you can work this through more in the details of the book is consider P, which is 0, 1. Sorry, what's the sign? I hope this is this is the right sign. This is an element of SU2, and then conjugation takes weight Q to minus Q. Okay, if you work out what happens to the weight when you conjugate by this matrix, you'll see that it takes the sets of weights to minus the sets of weights. So what this implies is that whatever the set of weights is, it's symmetric under change of sign. So you're going to have, for every one of a certain sign, you're going to have one of negative sign. Okay, so that was the second trick, of course, considering this guy. But now is where things get really difficult, is to make further progress. And to make further progress, you have to do something. So to go further, okay. So the problem is that you've kind of used the behavior of this one, you've kind of used the behavior of kind of rotation in one direction of that three direction, which is the U1, and you also need to understand what the other two, rotations in the other two directions are going to do. But the problem is that you can't do that simultaneously because they don't commute. So the trick is to go further. You want to go to the algebra. So at this point you have to stop. This is where you start needing to get away from nonlinear problems and down to linear problems that you can solve. And then what you do there, you find that. So what did I do? I said that S3. Okay, so I wrote in the Lie algebra I had x, x3 xj was, what did I do? It's minus I sigma j over 2, and that's the same thing as and then I had sometimes I would use sj's. So these were the ones I used when I wanted something anti-Hermitian. If I wanted something Hermitian, I used sj, which is just sigma j over 2. But that's I xj, right? Okay, so but now I can start asking, when I go to Lie algebra, I can ask about the Lie algebra representation, and what are these guys, what are these guys going to do to my representation? And then I know that and if you see that, for instance, so pi prime. So now I'm going to look at the corresponding Lie algebra representation, the infinitesimal version of the SU2 representation, and I found that my S3 was given by some integers like q1 over 2 down to q n over 2. Okay, and this was just some symmetric list of integers where whatever integers appeared here or somewhere in the list, you also had to have a minus sign. Same thing. But now here's the trick. This is what the really obscure trick is. You have to complexify. Well, let's just say define S plus is S1 plus IS2, and S minus is equal to S1 minus IS2. And now, so the thing is, you and then consider pi prime of S plus. Okay. And so it turns out the thing to do is the obvious thing to do might be to consider pi prime of S1 and S2, but those guys just don't commute with this guy, and there's not much you can say about them. The thing that does make more sense is to do something which seems to be a little bit funny from the logic of the whole story, that the Lie algebra, remember I was saying, was real linear combinations of things. Well, here I'm taking a complex combination of things by throwing in these i's. So this is not a linear combination of self-adjoint things, of real linear combination of self-adjoint things. It's a complex linear combination of self-adjoint things. So it's not self-adjoint actually. And one thing you find is that pi prime of S plus wait, how do I want to see? Yeah, anyway, pi prime of S plus or minus are not self-adjoint. So these are very weird. These you can these if you have a representation, you're going to have these operators in the representation, but they're not they're not self-adjoint operators. They don't have real eigenvalues. You know, physically, they don't have any obvious interpretation. And so they're funny things to work with. But they have this really nice property. Let's do this. Okay. So you can show, and here what you do is using so the one thing you have to get your hands on what's going on is you know that you've got a Lie algebra representation, which means you know that this pi prime map, which is some kind of linear map, and it preserves these it preserves the Lie bracket. So that the one thing that you have is that whatever this pi prime is, pi prime of a bracket of two things is going to be the bracket okay. So this is the Lie algebra homomorphism property. The only, you know, before you actually have your hands on the representation, the only thing you can do is keep using this property whenever you can in order to say things about, to learn things about these operators. And one thing that you find is that if if pi prime of S3 acting on V, so V is just some vector in the representation, that, you know, if it's an eigenvector, so it's k with let's say with k over 2 V, and so I mean so you know that it had, by the fact that this S3 generates that U1. This is what I was calling the QJs before, but k is an integer, so this is V. Here you say V has weight k. Okay. Then if you look at if you look at pi prime of, if you look at what either one of these operators is going to do to it, B. So you look at this guy. You hit this guy with these operators, which I constructed from these, and these are these non-self-adjoint operators. Then now this guy, you can ask what's the weight of this guy, and it turns out, so you compute this guy. Okay, and this is where you have, and to do this computation, this is where you have to use the commutation relation. Then this guy, then what you find is that this guy is k plus 2, k plus or minus, it's just plus or minus 2 over 2 times the same thing. Okay, so if this guy is an eigenvector of S3, so the beautiful thing that these guys are doing is they're taking eigenvectors. You know, they don't commute with S3, but they take eigenvectors with one eigenvalue of S3 with one weight to eigenvectors with a different weight, but of plus or minus, just with a change by plus or minus 2. Okay. Okay, and then to finish up, then what you end up with is this really nice picture of the representation. Okay, so what you do is you get you finally, you know, and there's some more work to do, but you get to this picture. Which is that you can analyze any representation, any finite dimensional representation of SU2, and what you can pick that subgroup, that U1, and then you can break it up into different weight pieces, and the pattern of weights is going to look like this. You're going to have some C, and I guess I don't want to write it this way. I guess let me write it this way. So this is C sub n. This is C with weight n as a U1. Right. Okay, and then we know that there's the pattern is that this has to be symmetric, so there has to be a C minus n somewhere. And then since this thing has to be fine dimensional, the list this list of weights can't go off to plus or minus infinity. So there has to be some biggest one. So we're going to choose this to be the highest weight. So we're going to assume that we're going to order these things here. So there's nothing higher than this, and there's nothing lower than this. But then what happens is then we find that because of this guy, if we act on things in here, if we act on these highest weight vectors by things in pi of s minus, we're going to get this n here, which was this weight here, drops down by 2. So you're going to have a C n minus 2, and you're going to have some linear map from here to here, which is pi of s minus, pi prime of s minus. Okay. And then you're gonna find also that then you can also study this and see that what happens is that you have pi prime of s plus takes things in here, things in here. And if you have a highest weight vector, you find that if you apply a pi prime of s plus to this guy, you're going to get 0. So. Okay. So one way of characterizing a representation is by knowing what its highest weight vectors are. Then you know what this n is, and you know that and you can, one way to get your hands on that is to look for solutions to this problem. Okay, and then but then you can figure out what the rest of the picture looks like. This is C. This is the same again, one-dimensional thing with weight minus n plus 2. And again, you got maps going this way and maps going this way. Okay. And then you just fill this in. Okay. And really this kind of tells you that you're gonna, anyway, you have to do a little bit more work. And this is where there's an argument in there which gets a little bit complicated, where you have to go in deeply and use the commutation relations in a fairly complicated and subtle way, and in order to show that nothing more, not to show that this happens, but to show that nothing more complicated can happen. But you can just using the commutation relations, you can show that this is the picture, and you can show that this is actually irreducible. That this thing doesn't split into pieces. That every you can get from any point here to any point in here by just hitting this guy with this guy often enough, and when you get down here, you'll get 0. Okay. So this is the answer. So maybe I'll stop there and just say so this is the spin n over 2 irreducible representation. This is it. But I mean, this should bother you a little bit, and because what I'm doing here, if you look at the structure of the argument, I mean, kind of what I've done is I've shown that if you I've kind of analyzed the pattern of weights, and I've shown that this is the only consistent set of weights, but I haven't actually constructed the representation. I haven't actually given you a mathematical object that with operators on it that you really can understand. I mean, but I've come very, very close to it. And one way of saying how close I've come to it is I've actually come to the point that if I give you an explicit construction of a vector in this space and an explicit construction of these operators, of pi minus s minus and pi minus s plus, then just by hitting this explicit thing with this operator, and enough times, then you will have an actual construction of the whole thing. But this construction comes very close to giving you a real construction that you can get your hands on, but not quite. And so what it mainly gives you is it tells you what the answer is to what the possibly reducible representations are and what their weight diagrams are. Okay, so let me stop here, and then next time I'll pick this up again. So what I want to do next time is actually give you a different, start a little bit differently. And let me just maybe say this here. So next time, we'll come at this problem from a different angle, and we'll get an explicit construction of all SU2 actually alternate representations as polynomials on C2. So if you look at it, it turns out you can actually very, very explicitly relate all these representations to polynomials on C2, and the irreducible representations are going to be are on homogeneous polynomials of a fixed degree. So we'll explain that next time. And then the next thing I want to talk about is what about SO3? And so kind of argue that whenever if you have an SO3 representation, it's going to give you an SU2 representation. I gave you that argument last time. So in particular, the SO3 representations have to be lying in this list, and it turns out the SO3 representations are the ones with even n or with integer spin. But it's often useful to think of the SO3 ones in their own language, to think of them as acting on something not in through SU2 and C2, but through something happening in 3 dimensions, and in SO3. And so I'll give an explicit construction of the all SO3 representation. And then the way to think about it then is really as functions on S2. Okay, so I'll say more about these next time. So that's the end. And if you look at the if you read ahead into this, I realize that there's something I was never very happy with about how I explained exactly how you go from a representation on a function like this of the group, and how you differentiate it and take a representation of the Lie algebra. So if you find in 1 or 2 places, if you find the explanation there confusing, it might be the place where I kind of agree that it's badly confusing, and I'm hoping to, one of my projects for tomorrow or the weekend is to fix that part of the book. So hopefully by Monday there'll be a less confusing, maybe you may find a less confusing version of it applied. But if you still find it confusing, definitely tell me, let me know, and especially by the next class, if I haven't unconfused myself about it by then, I got more work to do. But okay, so let's stop here. Are there any questions for now about the rest of this, about what we did today?
So Professor, S1 through S3 form a basis of the Lie algebra, correct? In the real version, or? Yeah, well, actually, so I mean, the way, I mean, yeah, so if you want these things to be unitary and for the operators to be skew adjoint, I would like to say that a basis, I would like to think of basis as is the the xj's, which are minus I sigma j over 2.
but for many purposes, it's and especially to make contact with the physics computations, it's better to just to work with these guys instead, because. But so it's true. So elements of the Lie algebra are going to be these guys multiplied by real numbers, or these guys multiplied by pure imaginary numbers.
Okay. And then S plus and S minus find the complexification
Right.
of the Lie algebra.
Yeah, because you're taking something which is self-adjoint, and you're adding something which is skew adjoint. So you've added, it's got two pieces, a self-adjoint piece and a skew adjoint piece. So it's not it doesn't have any adjointness properties itself, but it actually I guess what does happen, I mean, the way this is set up, a nice thing is if you take S plus and ask what its adjoint is, you'll find that it's S minus. So these two things they're not self-adjoint or skew adjoint, but they are each other's adjoints.
Okay, cool. And then does the pi prime, is that that's the derivative of the representation we're discussing, which is thus a representation on the Lie algebra.
Yeah.
On our space, right?
Or you can think of it as it's a representation of the algebra. It's a linear map from elements of the algebra to arbitrary complex linear transformations, and it has the nice and it's the thing which, if you exponentiate it, you'll get the SU2 representations. So pi prime is a thing, and if you exponentiate it, you get pi.
And that still preserves the Lie bracket after complexification.
Yeah. So the nice thing, this is the really nice thing about complexification, is that it that preserves the Lie bracket business. That relation doesn't know about whether you're looking at complex linear combinations or real or complex linear combinations. So those commutation relations you can generalize from the real case to the complex case. If they're true for the real case, they're also true for the complex case, just by linear algebra.
Okay, thank you.
Okay. Any other? Okay. Anything else? Okay, so again, then I'll cut this off, and anybody wants to come back and talk a little bit more, I'll be here for a while. Okay. Bye now.
Thank you.